A method we're going to use for factoring trinomials involves filling in a diagram that looks like one of these. Right now we don't see the connection to a polynomial, but we're going to treat it just as a puzzle. We're going to find two numbers that you would multiply to get the top value and that you would add to get the bottom value. So looking at this first example, we want two numbers that we would multiply to get 24 and that we would add to get 11. Sometimes these numbers just jump out at us. Other times we have to work a little bit harder for them. In this case, 8 and 3 work. Because everything is positive here and the numbers aren't very big, it's not very hard to just imagine all the factor pairs of 24 and find some that work. This works because 8 times 3 is equal to 24, and 8 plus 3 is equal to 11. In this second example, we have some negative numbers, which means we have to do a little more thinking. So the important thing is to look at the sign of the product first. Because this 27 on top is negative, the product, remember, is the result of multiplication. That had to come from a positive number multiplied by a negative number. So thinking about the signs first helps us to figure out the correct values. We now want a negative number in a positive number that we would add together to get 6, which means we're really looking for two numbers we would subtract to get 6. That helps us identify that 9 and 3 work. We know that the 9 should be positive and the 3 should be negative, so that when we add those together we get a positive 6. So positive 9 times negative 3 does give me negative 27, and positive 9 plus negative 3 gives me 6. One of the things that makes factoring a little bit tricky is that there's a lot of pattern recognition and coming up with numbers that we can't come up with by a formula, really. We have to try to recognize them or come up with an algorithmic approach that's going to get us to see every possible factor pair in those cases where the numbers don't just jump right out at us. The way that we're going to employ this to help us factor polynomials is what's sometimes referred to as the AC method or the grouping method. So if I take a polynomial that has 3 terms, it could be of the form ax squared plus bx plus c, that's the one variable version, or it could be the 2 variable version, which also is in descending powers of one variable. So this is descending powers of x. As long as it's in descending powers of one variable, then it's in a good order to identify your a, b, and c. So looking at this example here, we see that it's in descending powers, and therefore my a is the coefficient of the first term, so a is 6. B is the coefficient of the middle term, so b is 11. And c is the constant term, or the coefficient of the last term, so c is 3. The diagram tells us that I put a times c in the top of the diagram. In this case, that would be 6 times 3, so I'm just going to write 18 in the top of the diagram. I then put b in the bottom of the diagram, and b here is 11, so I'm going to write 11 in the bottom of the diagram. And now it's time to find numbers to fill in the left and right that are numbers I would multiply to get 18, that I would add to get 11. In this case, it looks like 2 and 9 work. So my diagram is now done. What I'm going to do in the next step, and first I'll write out the polynomial just a little bit bigger so that I have more space to illustrate what I'm doing here. I have 6x squared plus 11x plus 3. I'm going to write my polynomial again, leaving the first term alone, and also leaving the last term alone, but breaking apart my middle term into 2 separate terms, using these 2 numbers here as the coefficients. So I'll write it as plus 2x and plus 9x. So I'm taking the numbers from the diagram and I'm taking the variable part of the middle term and copying it into each term. First, and very important to verify, is that I haven't changed this polynomial. I've replaced 11x with 2x plus 9x. If I were simplifying, I would combine those terms to get 11x. So this is the same polynomial. However, it is now written as a 4-term polynomial, and so now I'm going to employ the grouping method, where I group first 2 terms and last 2 terms, and take a GCF from each group. 2x out of the first group leaves me 3x plus 1. And taking a 3 out of the second group also leaves me 3x plus 1. So I can see that I get a common binomial. And now I'm ready to factor that common binomial out in order to get my final factored form, which is 2x plus 3 from the GCFs, which make up my blue factor, times 3x plus 1 from the common binomial, which makes up the black terms in my second factor. So anytime that we factor a trinomial, we can use this basic process. It's going to be the same process for different polynomials, even though the polynomials might get a little bit harder to factor when we start getting some negative numbers and perhaps some bigger numbers than 18 that have more factor pairs to consider. Other than that, it's going to be the same process every time. Going on to our next example, 4x squared plus 4x minus 3, we again start by identifying a, b, and c and filling in the diagram. A is 4, c is negative 3, so that product is negative 12. B is positive 4, so in the bottom of the diagram I'm putting positive 4. Now for my numbers on the left and right, I can see that my product, negative 12, is negative, and therefore I'm going to need a positive number times a negative number to fill in this diagram. Positive 6 and negative 2 work, so I'm ready to go ahead and break apart the middle term in my polynomial. Remember that the first term stays the same, the middle term gets broken up into 2 separate terms, and the last term stays the same. And now I am ready to group. 2x comes out of the first 2 terms, leaving 2x plus 3. Negative 1 comes out of the second group. Remember that it's very important to factor out a negative number if the first term of the group is negative. And also it's important to factor out a 1 when we're factoring by grouping if there are no other common factors. And I see that I have a common binomial of 2x plus 3. Finally, writing my factorization as 2x minus 1 times 2x plus 3. Next, we'll take a look at a 2-variable example. This is in descending powers of x. It goes x squared, x to the 1, and then finally the term with no x. So this is in the appropriate order to go ahead and pull coefficients and plug into the diagram. On the top, I'm going to have a times c, which is 6 times negative 12, which gives me negative 72. And on the bottom, I'm going to have the coefficient of the middle term, which is negative 1. Again, I can see that I want a positive and a negative, so that when I multiply these together, I get a negative product. And for some people, these 2 factors will just kind of jump out quickly. If they don't, then all we need to do is start writing out all possible factor pairs of 72. 1 times itself is always a factor pair, and then start increasing the 1 one at a time. So 2 goes into 72 36 times. 3 goes into 72 24 times. 4 goes into 72 18 times. 5 does not go into 72. 6 times 12, that's the product we did to get it. 7 does not go into 72. 8 does. 8 times 9 is 72. By the time you get your numbers really close together, like they are with 8 and 9, or if they were to pass each other, then we know that we're done with our list. If we were to keep going past that point, we would just generate the same list over again written in the other order. In this case, it looks like 8 and 9 are my winning pair. I'm going to make 8 positive and 9 negative so that when I add these together, I get a -1. So the sign of your sum kind of determines which of these two numbers, the bigger or the smaller, is going to be the negative. All right, so convincing myself that I did this diagram correctly, I now come back to my polynomial and rewrite it. 6x squared stays the same. My middle term minus xy is going to be replaced by plus 8xy minus 9xy. And my last term, negative 12y squared, will also stay the same. And now I am ready to go ahead and group. Remember, when you're breaking up that middle term, that even though you're taking the coefficients out of the diagram, the variable part of the middle term always stays the same. We want the entire xy present in both terms so that they're like terms that would combine to get you that middle term. Now we take out a 2x from the first group, leaving us 3x plus 4y. And we take out a negative 3y from the second group, leaving us again 3x plus 4y. Common binomial is 3x plus 4y, so this does factor as 2x minus 3y times 3x plus 4y. So even these two variable versions really aren't any harder as long as we recognize them. Remember to have them in descending powers of one variable, and we go ahead and just break up the whole middle term even though the term itself has two variables in it. Incidentally, a question that often comes up around here is whether or not it matters what order we write those two middle terms in when we break up the middle term. The short answer is no, it doesn't matter, but I'll go ahead and work the problem out the other way so that you can see how it's different and how it still comes out to be the same answer. Looking at this, we see that we do have the same factors written in the reverse order, but we also notice that in our first example, the 2x and the minus 3y came from the GCFs, whereas in the second example, the 2x minus 3y is my common binomial. In the first example, the 3x plus 4y was my common binomial. And in the second example, the 3x and the plus 4y are my GCFs. So the problem unfolds in the other possible way to get the same factors. But it does end up with the same factorization, and the order in which we write our factors does not matter as long as it is the same factorization. So it doesn't matter what order you put those middle terms in when you rewrite your polynomial as a 4-term polynomial. It should work either way as long as you got the numbers correct.